Today I'm going to present the final findings of our summer project. Given the current COVID pandemic, the efficiency of the healthcare system has been brought back to the public. Among all the relevant topics, ambulance dispatching is always heatedly discussed. In this project, we focused on optimizing the ambulance dispatching policy in New York City. We want to answer the question whether sending the closest idle ambulance is always the best policy. Here is a brief summary of the dynamic process of the ambulance. First, a call is received when an incident happens, and then the dispatching system will make a decision and assign an ambulance to the scene. After picking up the patient, the ambulance will carry him or her to the hospital and then go back to the base. Our goal is to minimize the average response time, which is defined as the time from receiving a call to an ambulance arriving at the scene. We want to understand what policy could guide us toward this goal. Basically, there are two popular directions of ambulance deployment study. One is the ambulance base optimization, and the other one is the ambulance dispatcher system. The first helps decide whether the layout of the ambulance base and the amount for city to maximize the coverage of ambulance. While the second one focuses more on deciding which ambulance to be sent in order to minimize the response time or minimize the rate of overweighting. Our project belongs to the second type. In our project, we make assumptions about ambulance base location that is generated from the New York City polygon and the number of each type of ambulance in the base. We also make assumptions about the hospital location. Moreover, we assume that the time spent at the scene and time spent in the hospital follows exponential distribution. We got data from the city of New York with EMS incidents and selected the data from 2019, April, as an example. We divided the patients into two types, non-COVID-1 and non-COVID-2. And we also divided the ambulance into two types, ALS and BLS. Next, we come to the data processing. As mentioned above, there are two data sources. One is the EMS incident dispatch data, which contains information about each real incident in New York City. And the other one is syntactic data, containing information about hospitals and ambulance bases. We first did some data cleaning, including analyzing the missing pattern and decided to keep three useful features: incident timestamp, initial severity level, and the zip code. We also standardized the time format in order to fit it into the discrete event simulation model. Since no exact incident location was provided, we generated a random pair of longitude and latitude within the zip code polygon area for each incident. And then we merged the EMS incident dispatch data within the syntactic data and fit them into the simulation model, and use the initial severity level of each incident to decide whether an ALS type ambulance is required. We have a baseline model and a hypothesis model. In the baseline model, for non-COVID-1 patients, we always dispatch the closest available BLS unit if there is any. Otherwise, we dispatch the closest available ALS unit. For non-COVID-2 patients, we always dispatch the closest available ALS unit. This policy looks reasonable and actionable. However, the baseline model might result in significant ambulance inefficiency in busy areas, leading to extremely long response time. Therefore, built on the baseline model, we suggest another policy. This time, we still dispatch the closest available ALS unit for non-COVID-2. Well, for non-COVID-1 patients, we dispatch the closest available BLS, if any. Otherwise, we dispatch the ALS if we only have one ALS left. If we have more than one ALS available, we randomly dispatch top two ALS. This is for the purpose to prevent no close ALS for severe emergencies, but the randomness provides less explanatory power. Here is the result. We compare the baseline model and our hypothesis using the simulated data and the real data. In both cases, our hypothesis model performs worse, showing a longer average response time. With the simulated data, the ambulance utility increases a lot, which makes sense since we are not always dispatching the nearest one, but make full use of all ambulances available. Overall, the result shows our hypothesis model is not as effective as the baseline model, which is good to know. Although the baseline model is widely discussed, there are more other dispatch policies for us to explore. Here is a summary of some literature and policies mentioned. It is worth mentioning that there are more and more studies focused on the dynamic dispatch process, which has involved the market decision process method. We also dive deeper into two of them based on our interest. Although we didn't implement it in our project due to the time and effort limit, the brief summary of the two literatures is appended at the end of the slides. Thank you for your listening.